Okay, so let's get started for today. Today's class will be about seam carving, which is, I think, a pretty neat, very interesting algorithm in computer vision that allows us to do some useful things. It's actually implemented in a variety of different commercial products like Photoshop and others. You may have it may be labeled something like intelligent zoom or something like that. But here we'll go through the implementation as step by step from the ground up. And secondly, I like the algorithm because it's a very nice example of dynamic programming, which is a very important, very powerful problem-solving strategy that can be applied to many different problems. And as such, just knowing about dynamic programming is also an important part of this class today. So let me just align the thing a little bit better maybe. Okay. Okay, so let's get started. I created a couple of images. So let me first post the lecture slides. They're again available as Jupyter notebooks on my Google Drive. And the link is here. So here we have an image of Lotus Lake in Kaohsiung in Taiwan, and if I zoom that picture, then you can easily see that as the size decreases, we lose a lot of the detail in the image, and it's very hard to see anything still in the particular image. So a lot of detail is lost when we're resizing the images, and the idea of seam carving is that instead of simply reducing every part of the image the same, we want to do that intelligently, with the idea being that we focus on the interesting parts of the image. So if you look at this particular image, then the things that would stand out would be the pagoda here in the front, right? That part of the image, as well as maybe the temple here in the background, the part that is red. Everything else is of lesser importance. Right? So now what I would like to do is implement an algorithm. For example, the sky here is not really adding any information to the picture. So what I would like to do is for the algorithm to maintain more information about the pagoda and the temple in the background here and maybe part of that bridge. And instead reduce the amount of information, the part of the image that is the sky, because there's not that much information in there. So somehow I would like the algorithm to focus on the interesting parts of the image. So now the question is, even though that the description is very straightforward, the main problem is how do we instrumentalize, how do we make a constructive theory of what we mean by interesting? If I show you that picture, then most of us would agree that this would be the main part of interest in the image. But how does the computer know what the interesting part of the image is? Now, that problem has received a lot of interest in computer vision over the last 40 years. That's usually called saliency of the image, and then we use that kind of notion in order to, for example, cut objects out from the background or things like that. Here we use a very simple model of interesting, a simple definition. But you can see later on that the seam carving algorithm can also work with more complex descriptions of what we mean with an interesting part of the image. So first, we can think of the concept of interestingness, or whether something is interesting or not, as sort of a measure, proxy measure of the amount of information that is associated with a single pixel. And for a simple theory would be to say, well, a pixel is interesting if it's different from its background, if it's different from its neighbors, right? So one could argue that if there is a uniform colored shape, like everything is red, like a stop sign, then each individual pixel within that stop sign is really not that interesting. Similarly here, for the sky, the blue pixels in the sky really are not much different from its neighboring pixels. So we can then say that we measure the interestingness of a pixel, we approximate the interestingness of a pixel by how different it is from the background, from its neighbors. And of course, I can think of pictures where the interesting pixels are not the ones that are different from its neighbors, but the ones that are actually inside of the image. Like if you're filling out a shape with something that shouldn't really be filled out, then those may be interesting pixels. Like say if I have a picture like this, now we paste that picture in. And here would be a stop sign. Now you can say, well, these red pixels are really not interesting, right? Because they're all the same. Okay, fine. But if I do that, should have used a different sign, but stop, slop, pop, stop, stroll. if I now do that, if I now do this, then you could argue that these pixels now are interesting because they changed the stop sign. But without having a world model about what the stop sign should look like, there's no way that I can do that kind of processing, that kind of reasoning, just looking at the individual pixel. Right? This would require some very high level knowledge about what this is and what it's supposed to look like, and now the pixels that are missing all of a sudden become important. That's extremely difficult, certainly not something that we can solve in the general case. Let me can I delete this? Hmm. Unknown amount. So here the missing T is something that, unless you understand stop signs, you'll never be able to say that these are interesting pixels. But in general, one would think that the difference of a pixel to its background, to its neighborhood, would be an indicator of the interestingness of that pixel. So we're going to investigate this idea a little bit and then see what we can do with that. So how our image at the moment is 474 by 323 pixels. So we can take the picture and first convert it into grayscale and divide it by a factor of 3, let's say. So this is the output of our image when I divide it by a factor of 3 and then just post it in. So you can see that we lose a lot of the detail already. Let's try and make it a bit more extreme. Let's divide it by a factor of 4. And also that's no here. I think I just set the factor to 1. Oh, why is it a color image now? I think in this case the format of the image is incorrect, so I just convert it to grayscale, just using the green channel. Oh, I don't need to code that much. Ooh. That would be colon, colon, colon 1. Yeah, so here's a grayscale version of that image. So now first we're going to calculate the gradient of this picture. Now I can do that in 2 ways. One is, since my definition was about how much difference there is between the picture and the pixel and its background, this would be the slow version of calculating this. We go through the entire image and we then look at the 8 neighbors of our pixel. -1, -1 would be the top left one. 0, -1 would be the one on top. 1, 1, -1. So this would be X and Y offset. So 1, -1 would be the one to the right and on top. This is a left neighbor, this is a right neighbor, and these are the 3 bottom pixels, the pixels below myself. Then I check if those pixels exist. If they're within the range, then I take the difference, the absolute difference between the pixel itself and that neighbor, and then eventually I sum them up. Well, why would I use... If it's a color image, then I do that for all the 3 channels. And then I can calculate the average interestingness by, I need to know how many pixels I actually divided by, and this calculates the average difference between that pixel and the neighbors. But we already looked at calculating differences between pixels. And that means we know how to do that significantly faster by using the Sobel edge detection algorithm, right? Because that calculates the first derivative of the pixel, the image function at the pixel location, in the x and the y direction. So that I can calculate the gradient, then I can estimate the gradient based on the partial derivatives by getting the square in here. This should actually be mass dot square root, but since we look for the maximum values and since square root is monotonic, that means if x squared is bigger than y squared, then also the square root of x squared would be bigger than the square root of y squared. So I don't actually need to calculate the square root. I can speed up the computation a little bit. So let me see if I can write that using math notation. I think it's delta actually, just delta. Yep, so that's correct. Nabla. So here are the definitions. So then the magnitude of the gradient no fraction, no. Hmm. So here we approximate the magnitude of the gradient then as Sobel x squared plus Sobel y squared. And just for completeness, we won't actually need it in this particular the direction of the gradient we can approximate that as the inverse tangent of Sobel x, where this should just be a-tan mathematically, but if you implement it on a computer, it's good to remind yourself that you really want to use the a-tan2 function. It saves you a whole lot of trouble. May save you a whole lot of trouble if you're dealing with vertical lines or lines that go through all four quadrants. So that means we can implement that algorithm just using the Sobel edge detection. So I can calculate Sobel edge detection in the x direction, and the y direction, and then calculate the magnitude. And then, just out of interest's sake, we're going to print out the minimum and the maximum of the gradients. And I can then apply square root to all of those. Or I could just return C here. So we get the image, we divide it here by a factor of 1, because the image is not big enough that I actually need to zoom it out, and then calculate the gradient. So it goes from 0 to 97,000. We can also display that image. And what do I want to plot? X1 dot show image G. Oh, I do call false color image. Draw image. What did we? Image show. Yes. How come it's not happening now? Ah, yes. Ah, wrong image. The stop sign is not what we wanted. So I need to change. First I need to run this. Image 1. Okay, yeah, so this is image 1, 2. Okay, these are the right images. Okay. Come on. What do I call it with? Ah, yeah, okay. That's the problem here. So I don't want to download it again. And that would be here. So here's the output of our gradient, the magnitude of the gradients. You can see not much in the sky at all, quite a few details in the pagoda here, also on the bridge, that temple already a little bit in the background. The skyline here also have a couple of strong gradients. So here we can normalize the image in order to scale it to 0 to 255, and have a look at the output here now, after we normalize the image. So now, when I do the zooming, what I want to do is I want to remove a string of pixels, right? Because I want to shrink the image. So first we're considering removing one column, and then afterwards we can see how to remove one row. But basically resizing the image is an iterative process. It's a loop where we keep removing one column from the image. Now that column should be connected, so I don't want to pick random pixels in each row, because then the image things would shift along each other. I want the sort of topography of the image to remain the same. So that means I want to start at the top, anywhere here, and then when I remove a pixel, then I want it to be one of the three neighbors below me. The bottom left, bottom, or bottom right pixel, and then we go through. So it should be one band of pixels, the set of connected pixels that I want to remove as one column. But it doesn't have to be a straight line, right? It's possible to be a squiggly line in order to stay, and the idea then would be that we remove the most uninteresting pixel. The least interesting pixels should be removed from the picture, but not but in that case we need to know the interestingness of not just a single pixel, but the whole chain going through the image. And that means we need to calculate, that turns it into an optimization problem. I need to figure out from any one of the start pixels, I have choice going down, left, going down, or going down to the right. And for each one of those, then I have another choice, right? And then I make, let's say I decide to go straight down. Now I'm at a new pixel. Now I can choose again. Bottom left, bottom or bottom right. Then I go bottom right, then I can choose again. I want to find the chain of pixels that minimizes the gradient, that minimizes the interestingness of the pixels. So that's why that string of connected pixels is called a seam. It's kind of like a seam in a garment, in a piece of clothing, and we want to remove the seam that has the least amount of energy, the minimum energy seam. So first we need to find the minimum energy seam, and then we have to remove it. So now, when we think about the runtime of this algorithm, then at each point in my evaluation, I have three choices. Let's say I even know where to start, and I start in the center of the pixel. Somehow I know that. Then I have three choices to go to row number 1. So now I have 3 possible successor pixels. If I now pick one of those pixels, then I can have another 3 choices. And the middle one has another 3 choices. And the right one also has 3 choices. So at the second level, first level I have, at the 0th level I have 1 choice. At the first level I have 3 choices, 3 leaf nodes. At the second level I have 3 times 3, 9 leaf nodes. Next level down I have 9 times 3, 27 leaf nodes, so on and so forth. And so you can see that the possibilities grow very, very quickly. If I were to follow this particular algorithm, then the order of the algorithm, the big O notation of the algorithm, which means the worst case, the lower limit on the worst case runtime of our algorithm would be 3 to the power of h. Now that doesn't sound like such a huge number, but we have images, so h is actually quite large, right? Here I have 321 rows. So that would mean here the runtime of the algorithm could be somewhat approximated by 3 to the power of 321. And even though that may not sound like a lot, it is actually an extremely large number. It's astronomically super, super big. It is vast. 2 to the 100 is the number of estimated number of electrons, protons, and neutrons in the entire universe. Every star, every galaxy, every grain of sand, all the electrons, neutrons in the entire universe is approximately 2 to the 100. So now you're talking about 3 to the 300. That makes 2 to the 100 look like an extremely tiny, small number. So for all practical purposes, this is infinity, and there's no way to calculate that size, that algorithm, using what's called an exhaustive search algorithm. And it doesn't matter if you use a computer, a single computer, a laptop, a workstation, a supercomputer, a super computer, or anything else. It will take gazillions of years to find a solution for that particular problem. So how do I, maybe 2 lines? Not H2. Ah, like this maybe. Yeah, okay. To showcase that, here I plot the complexity for a function from 3 up to a pixel, an image that has 20 rows only. So that's a tiny thumbnail, really. The number of leaf nodes for an exhaustive search algorithm would be 1.2 billion nodes that you would have to expand. So using best computers, that's possible to evaluate through, but for 300, the main point is to look at these computational, the runtime algorithm, and if you have exponential complexity, then what will happen is that basically your runtime grows into a wall. So you can see this just goes up towards infinity now. So here 17.5, you may be able to still calculate that. If you want to go here and you get vastly more computing resources, then maybe you can still move up here a little bit. But if you're now talking about 300 is on the other end of my laptop screen. There's just no way that you will get over this wall of the computational exponential complexity. So that approach will not work. The exhaustive search will not work for finding the minimum energy scene. What we can do is actually let's move that one up. So one solution to that problem may be to use a greedy algorithm. And the idea would be that every time I have to make a choice, if I look below and I have 3 pixels that I can move to, having gradients of 10, 52, and 5000, then you may think, okay, I move to 10, because if I want to find the minimum, it doesn't seem to be smart to move towards the higher numbered gradient. That's called the greedy algorithm. At each step in our processing, oh, I need to switch the screen. Each step of our processing, we go to the best looking neighbors. Here's a picture of the computational complexity graph that I just showed. And if you missed it, here's a picture of the gradient map for that image of Gaussian. And sometimes a greedy algorithm can actually work, or it works quite well. Those algorithms are extremely fast because each step I only need to look and consider 3 possibilities, then I make a move, but then I never consider doing any kind of backtracking. However, this greedy approach is not guaranteed to find us the globally optimal solution because it may be misguided, and in particular for this domain with images, the greedy algorithm is usually not good enough. So for example, if we look at the picture here, then I may start here at the top and I follow the seam, so now I have 3 neighbors. If the neighbor on the left here is 5 and this one is 7 and this one is 6, then my algorithm would move to 5, right? And it'll stick here. But the problem is, once we're here, we cannot, there's a lot of high gradient pixels here, so I cannot cross over here anymore. So the algorithm will move down this way, and then here we're stuck now. There's no way to avoid going through these high gradient pixels. So the algorithm may follow this path, the greedy algorithm may follow this path, end up with a sum over all the gradients in this seam, which is much worse than the seam that we get by following here to the right. Clearly, this part of the image is the one that we would think we want to remove. You can also see there's a lot of very low gradients here. But if we pick this path, then there's no way to go across here anymore. So the algorithm is just going to go down, and now here we're stuck. We just have to go through one row at a time. We end up with some minimum, some energy here, which is not the optimal path that we would find going down here this way. Let me change this one here. So dynamic programming to the rescue. So the technique was invented by Bellman. Let me check. In the 50s. Just want to see if I can post links in here using Markdown instead of HTML. Not sure why. Do I need to do it this way? Now, in order to apply the main idea of dynamic programming is that there's a set of subproblems that are being reused so that we can cache them. We can cache the solutions, which is faster than always recalculating it from scratch. And also there's a way to combine the subproblems efficiently into an overall solution. If those two features are given, then that particular problem can be solved using dynamic programming. Right. So we can see that there must be some overlap because our picture has how many columns? 441. Should be one. No, it's not image. Why? It's all image. 474 columns, but 3 to the power of h is vastly larger than this, right? It's much larger than that. So some parts must be counted double. In general, our problem structure is a graph and not a tree. So if this happens, that the worst case complexity that you calculate and estimate using a tree structure is vastly larger than what it could possibly be, if you consider the problem structure, then that means that usually there are subproblems that must be recalculated, and then if you can cache the solutions, you can save an enormous amount of work. So here let's try and create a table, a random image with some pixel values. And then let's calculate a couple of paths and their energies that we get. So for this picture here, if I take path 0211203040, that means we start at column 2, then we move one row down to row 1. Row 1 we move to column 1, then row 2 we move to column 0, and then we go down column 0. I end up with an energy of 255. So we started here 76. Maybe I'll make that smaller. Let's only do 4. No, it doesn't really make them bigger. So here we have 041424, then 3343. So I start 01234. So we start with the 71. Then we go down 37, so we have about 108. 108, then we go down one more, 12, 108, 110, 120. And then we move to 33 and 43. So that would be this one here, 63. 120, 184, 185. I calculated 184. Okay. Just ended up one incorrectly. So that's how we end up with the energy for the seam. And now using this program, I can just generate some random path, random seams, and then calculate their energy. Now, that sometimes that is a reasonable solution to a problem if your space, if your solution space is very flat and there's many possible solutions, then of course a random guessing algorithm, a generate and check algorithm, will probably work quite well, because you'll find a good enough solution very quickly by just doing random guesses. The images are not like that, but some other problems, this problem solving approach, you should also keep at the back of your mind, because it's very easy to implement, and sometimes it can lead to good enough results very quickly. So then we can implement our greedy algorithm. So I call that greedy seam algorithm. For that particular table, it actually finds a seam with an energy of 163, which is not as good, definitely not the globally best solution, right? Because this particular path here that I just generated randomly, I already have one that is better than 163. This one here only has a cost of 155. So if I cut that path out, I only need to pay $155. Then that's better than having to pay 163. But here's the implementation of the greedy seam algorithm. We take the image and set the minimum and the index for the minimum, and then first we go through the entire first row. So this is row number 0 here, and we pick the pixel in the top row that has the minimum amount of energy. So at the first stage, we don't really have 3 choices, but we have 441 choices, right? I can start my seam at any column. And so we go through, we pick and remember the one with the minimum energy. Then I set X, and this will be the start of my path. Row 0, we start at column X. Then for the other rows from 1 to the height of the image, I now look for the pixels below, to the left, down, and to the right. And I check which one of those has the minimum energy. Remember it, and then append it to the path. So this will generate the greedy seam algorithm here for the image only for columns 1 to 10. Why did I check 1 to 10? Because I wanted to find one where the greedy algorithm doesn't produce the optimal solution. So now dynamic programming, break a problem down into subproblems, solves the subproblems, and remember to cache the solution to remember or cache the solutions to the subproblems. Then, after you solve the ones that you need, reuse those solutions when solving the larger problem. Now, because of the fact that we're talking about subproblems and then generating solutions to the larger problem, that means that often dynamic programming is implemented using a recursive algorithm, but it doesn't have to be. Most modern implementations, it's more defined by the structure of the subproblems and the cache that you need in order to cache those subproblems. So then a lot of them are actually implemented using various tables. Now, other algorithms that are examples of dynamic programming would be Dijkstra's algorithm for finding the shortest path in a graph, Floyd-Warshall algorithm for path planning on shortest path problems, and the Levenshtein distance. That's the algorithm that calculates the minimum editing distance between two words, and it's what's running when your computer makes suggestions about spelling mistakes. So, for example, if you notes or just because it's an interesting algorithm to know. It's used in lots of programming interview questions for AI jobs and things like that as well. Seems very popular for that. Just to introduce the problem. Let's say I type doc. Now doc is not in your vocabulary. It's not an English word. And you want to now tell the user that I don't know this word. Maybe you made a spelling mistake. Maybe you meant to type something else. And when you do that, of course, there's the idea that the user really was trying to type house, right? But you would think that if I type DOK then and I wanted to type house, that seems like it's not very likely that that was the mistake that I made. Other forms would make a lot more sense to think that doc was a misspelling of dog, right? Or you may want to propose that dog and really they were trying to type cat. That would be also not very likely. So basically the idea is to figure out how many mistakes must the user have typed wrongly for doc to turn into cat. And then you can see what's the minimum number of things. Now, the mistakes that the user could make, of course, would be typing the wrong character. So you could have D versus C, or O versus A, or K versus T. But there could also be other mistakes like dosk. So the S here and the K were swapped and set in the wrong flipped around. So the Levenshtein distance tells us how many insert character, remove character, additions and changes we have to make in order for it to turn into the target word. So let's see how that works with seam carving. What are the subproblems and how do we store the solutions? How do we retrieve them? Now, if we look at the algorithm, then we can see that if the current sum from anywhere on top to this location has a gradient value of 2, and here it's 5, and here it's 3. So that means when I go upwards, instead of going downwards, I now calculate I store in a table the minimum path from that pixel to anywhere on the top of the image. Maybe I should. Yeah, here's the diagram. Okay. So if I have those numbers, then we can see how the algorithm progresses, because if the sum of the gradients on the top here is 2 and 5 and 3, then for this particular pixel, the cost is going to be 2. The minimum energy cost is going to be 2 plus whatever my own gradient value is here. So let me see if I can draw that. Okay, I have an animation of it, of the algorithm, but hopefully makes it clearer. Let me just... draw that image slightly nicer. So the gradient is equal to some random integers from 3 rows and 6 columns. Right. So let's see that that looks correct. And the integers are from 0 to 20. Ten to 20. So here's our gradient image, just the first 3 rows, a small example. So now I'm just going to plot that in an image. So for x, for y in this is now a NumPy array, so I could just do this. Height width is equal to grad.shape. And I just want to show the recursive step in this particular picture. The entire algorithm I'll show in a second. So I'll plot only h up to 2. Actually, let me see. So R is a rectangle, and the parameters for rectangle are X and Y as the top left coordinate. So there will be X and Y, and the width and the height 1, and edge color black, face color light gray. Oh, that will be dark gray, so E0, E0, E0. Then we need to add the patch. So then here that should show it. So here's an example of rectangle. The spell checker presenting it. How come this is only 1, 1? E6. That's the width and the height of the rectangle. So it should be 0, 0. Rectangle. X, Y, width and height. Yeah. I know. Yes, the problem is if you add patches, then Matplotlib doesn't actually draw anything, so it just shows you the first one. with the default of 0, 1, 0, 1 because I don't have any data that I'm actually plotting here. So in this case, I want to set the x limit to be from 0 to the x limit should be the width, and the y limit to the height. Yes, that's easily forgotten. So here's our rectangle now, with the individual cells, and I want to now that should be here. What I actually want to plot is height minus y. Height minus 1 minus y. So now we have this, and I now want to add the numbers. I draw the other ones. If y is greater than 2, the face color is white. Okay, and now I also want to plot the numbers. So now I plot the values for the gradient and the numbers for the sum. So ax1.text. So that should be x plus 0.1, y would be h minus 1 minus y, and then I want to shift it up a little bit, so 0.1. And the text I want to write there would be the gradient number. So that would be gradient gradient y comma x as 2 decimal places. Zero 2D, not percent. So now I have some numbers here, but not where I actually expect them. That's probably because I push them down too much. And that's for the wrong side. So here are the gradients now, and that's a little bit too much. So what I need to add is the sum So here now I have the sums. Actually, I can plot. So now let's say I have these values here, which are the sum of the values on top. Then how do I figure out what numbers to put in the bottom place here? That's the tricky question, right? That's a recursive step of the algorithm. So here, this will be the sum. And right now, I don't really care about how I get them. I just put in some random number in this position here. Okay, so how come it's not happy with that? That matches there. Format string. Yeah, here. So here I have the sum now. And now you can see the recursive part of the algorithm. If I now consider this pixel here, right, then my gradient here, my own cost here would be 15. But if I look at the sums, not at the gradient values, but at the sum values that I have, then I have 196, 112, and 122. So that means for this pixel, if this sum is correct, then I definitely want to continue the seam going downwards by connecting to the seam on here. And in that case, the cost for this particular pixel would be 112 plus the 15. So that's how I can extend from one row down to the next row. For each pixel in the next row, I can then calculate what the optimal seam cost is going through this particular pixel. So let's plot that. Oh, I don't actually have them selected. Now, how do I start this algorithm? Well, I would start it at the first row, and since the first row has no neighbors on top, that means that the sum would simply be the values of the first row, right? So the sum here would be 19, the sum here would be 11, 12, 14, 14, 19, simply because there's nothing on top. So using this data structure, this simple table, I can now know that the minimum energy seam will go through my top neighbor with the minimum energy, and the minimum energy path then for that pixel will be the minimum path through my top neighbors plus the magnitude of the pixel itself. So then we have then we can generate an algorithm which draws the array and returns the artist that used to draw that, and then I can do a little animation with that, and then that should be That will give you a nice visualization of how the algorithm actually works. So on the left hand side is our gradient magnitude image. Here's our cache. So instead of having them one above the other, I use two tables. And then we start by initializing the table with copying the first row from our gradient magnitude array. So this is the first row, simply copied across, because the first row has no neighbors on top. So there's no energy that needs to be fed through to the first row. But now for the second row, I now want to fill in the second row, and I want to fill in the second row with the cost of myself. Let's say I consider this pixel here. This pixel here would have a gradient of 73, gradient magnitude of 73. The cost of the minimum seam going through this pixel will be the 73 plus, and then I actually have two choices, either this one here, this 43, or this 43. Just happens to be the case that there's a tie. So it would be 92 plus 43, and then I can choose to go this way or that way. It will give me this, both will be optimal solutions if that pixel here is on the minimum energy path. Now I wanted to change that a little bit. And I want to draw this will be interesting. So let's try and improve that a little bit. So this would be height times width. And 3 neighbors that I need to extend. But then for the first one, I don't need to do anything. I just need to have one step. So that would be width times 3. So that would be height minus 1. and 1 for the first one. So if the step is 1, then here is the step. So where do I increase the step instead of I? So that will go through every frame. Yeah, let's try that, but I think I want to save that piece first. Let's try and see if we can do it this way. Star is equal to 1. So that means I need to break it down into 2 components. So first one is the first row, and then for the stages. Yes, so for stage in range 2. I think that should work. So now I want 3 steps, and I need to do that for every pixel. And then, oh, because they're different subplots, I won't be able to plot them in the same image. So that's, I won't be able to draw. I wanted to draw an arc from the one pixel, the one data item to the next one, but that turns out to be not so easy. So maybe it's better if I plot them one on top of each of another. So I stack them as a set of in a column. So the frame is 0, then frame is empty frame here. So now what do we need to draw? We need to draw the array, x limit, y limit. Oh, yeah. But it's nicer to draw it with two arrays. I also noticed that. So that means we need to have a new draw array function. No, I think that will be too complicated to try and do that animation the way that I wanted it with the arrows flying around. That will take a while to program that. So I think I'm going to leave it at that. See, where's previous? Here. Yep. No, I think I need to draw it as just one array. Then that will be actually better. So let's take this one. And I will plot plot the as one array. And then I have the previous array. So if we're in the first stage, then for every column I need to draw the arrow moving them, right? So I want to draw the array. But that means I need two array here. And the image that I want to use, T1 image, where's that from? That is here. But now I need two numbers there, not just a single number. So how do I do that? That's some zip message. 0 to 99 for the gradient, 5 by 9 array. But now I need two numbers. And I set the second one to -1. So then let's see what that looks like. Oh, no picture. 21 minus 1, 71 minus 1, okay. So this would be first row, second row, third row. And here I can now define gradient and sum is equal to range 2. So that when I access them, I don't make a mistake. This kind of like defining enums in Python. Dot shape, height, width, and the last one I don't care. So now we have two stages. In the first stage, I want to just copy the gradient value into the sum for the first row. So for the first row, I step through, and I think I need first row should just be plop and then move it up, so it should only be 2. So I want to draw the array, and the array that I'm drawing is the axis, the array, and the previous array that I have. And the previous array. And now, when I draw the array, I need to draw two things. Here I don't draw it using rectangles. Here I actually use ax.plot to draw the grid pattern. Okay, so this means this, and then now I want to draw the sum. Here I draw the gradient. Here I draw the sum. And the point here, I want to draw it on top. And here I take 0.5, 0.05, and here I pick 0.5. Oh no, other way around. 0.5 and 5. So let's see what that looks like. Then we can extend the artists. And pentaframes. But I need to draw the whole thing, so this means this draws the whole square, whole rectangle. I think nothing else to do, right? Yeah, probably works. So this is what I need to delete. Right, yep. And then the other problem is we have to make sure it doesn't use too much memory, because when you're generating animations like that, then that can also cause problems. If okay, get rid of the printing. Oh, nothing actually. The image of 0, x, sum is equal to t image 0 x gradient. So that sets it. So now we're painting the gradients. Oh. God, that's correct now. So don't need to print that out anymore. Oh, scroll too far. And the sum is a little bit too far off to the right, left to the right, so let's make that 0.4 and 0.1. So here we have gradient 66 and then sums are initialized correctly. So if I look at the animation, and it's Annie 23. Oh, that's rather small. Frames dot append frame. So now here it plots in our sums. And actually it should plot all the It should plot all the gradients. So this part here, the gradient needs to be out of the if. And then append it. And let's try that. So here we have the gradients. And then we're filling in the first row. Oh, we actually have a gradient of 0 there. Okay, so that's our first row. Now I want to the steps. If it's 0, we do it this way. And I need to draw that first, so otherwise it's going to overlay it. Patches dot arrow. XY dx dy. So xy would be the arrow should go from x to y, Now y would be that minus 1 minus y. Five, and then 0 point dx 0.5, 0.5, and face color is equal to red. Let's add that artist and frame dot append arts dot append no frame dot append want to add that arrow, so let's see if that works. Okay, sort of. Just a little bit too thick, my arrow. So let's go with width is equal to 0.05. Let's try that, and here I need to update the previous array, so that would be here. And I need to copy that array, so that will be C for C in T image, R for R in C for C in R for R in T image. I think that's it. Okay, now we have a really small arrow, so maybe a little bit too small. So x plus 0.1 x 0.5. Okay. Rectangle object, T image. I think it's like this. In R, for R in T image. Now my arrow is okay. Then now it's too high, so maybe plus 0. That's the position. The position is okay, but dx dy, so 0.3. So now we have this. Can make that a little bit wider. So that takes our sums now. For the first row. So that's pretty cool. Now we need to go to stage 2. So now I need to update the sum for the next row. That would be the three neighbors that I look at. So if x plus dx is greater than or equal to 0, and x plus dx less than width, then I can update the value. I also need to keep track of the minimum. The minimum. Value would be t image y minus 1 x dash is x plus dx xt sum is plus t image y. Now I need to add my own gradient to it. So if t image yx sum is equal to minus 1, which means we haven't touched it yet, or t image yx sum is greater than the value, then t image yx sum is equal to the value. We update it. And that should do the rest of the array. And then we draw the frame. I need to copy all of that. So we draw the array. I won't do the step just yet. Well, we need to do this. Okay, then let's see what that does. what's wrong with my indices? The t image yx sum is equal to minus 1 or t image y sum yeah, now it is a little bit slow. Drawing the generating the animation, so let's see how fast it is playing it. Then I go through all three possible neighbors. That's actually correct. 27 plus 43 is 70. So I go through the array. And so each number here is calculated as this one here will be 69 plus the minimum of 41, 69 and 15. So that should be oh, this is 150 here. 69 plus 41, 110. Now pick the right one. So depending on which number it goes through. First one that it tried was this one here, and then the remaining ones. 20 is 35 plus 35 is 20 plus 15, so on and so forth. Here you can watch the old animation the way that I had it before. But it doesn't show the relationship quite so nicely because you're missing the gradient. Like you need to look on the left side and then add that up here. So this pixel would be 30 plus the minimum of 135, 116 or 45, where the minimum is 75. So once we have the table filled out like that, then our next problem is we need to still find the minimum energy seam, but that can be easily done because if I look at this pixel here, for example, 133, if I look at 133, then I have to move up here because this will be the minimum energy seam pixel that I need to go through. So I don't actually need to store the path that we have going through the image here. So for this dynamic programming cache, any pixel that I have, I know which way to go. Right? Right? Down here we need to look for the minimum. So the minimum energy seam that I get is 107. 107 has three possible ways to get to 107. This way, or this way. Then obviously we came from 106. From 106, the next one would be 75. 75, 63, 63, 45. So on the way backwards, I simply need to look for in the sum table, I need to look for the neighbor that has the minimum energy. That's the movement that I have to make. That way I can extract the path from the system. And then that will be the solution for just the small one that I just made, the small image. So let's see. So here we can look for the path. And I can also compare the greedy path and the minimum energy path. And then plot it. Now I need carve. Using the gradient image. Right, so I need the gradient image that I need to recalculate. I must have overwritten that. Yeah, here I overrode it, so I need to get the original image back. Gradient. Yes, the carve values, which now show places that have very high energy going through with the column, and then we can find the path. And this would be the image. So here's the and I didn't do the swap of RGB values, but actually it's kind of interesting to look at the false color image. Here's the minimum energy path that is removed from the image. So now I can apply that, but I think that may not work now. Draw array old. So here's how we calculate going the entire carved array, the scene that we want to carve, the sum array, and then how we find the way backwards to the minimum energy path from this table on the right hand side. So our table updated, and then we can go through 136 would be the minimum here. So 136, 121, 108, 44, 33 would be the path that is cut out. Oh. I have the wrong gradient now. Because we didn't calculate this here. Yeah, let me try if I think I just need to call the old one. Too many values to unpack, yes. So never mind that part. So now we can compare find the minimum energy scene path and the greedy path for the image. Make sure that we have the image correct. And on that particular image, we can see here is our minimum energy path. Here is our greedy path. So the greedy path would have actually cut off this area here, which actually is quite interesting. Much more interesting than this whole lot of blue sky here and lake. So then we need to implement a function to remove the path from the image so that we can actually shrink the image, right? So after running it now, image now has 321 columns, 321 rows, 474 pixels before, and the new one will have 473. So then I can implement a subroutine that repeatedly cuts out a path so that I can shrink it by more than a single row. Also, one way of doing that part of the image is, instead of writing two routines, one for the column, the other one for the row, we can simply take the image, rotate it by 90 degrees, and then extract another column. So then we don't need to write two different versions of basically the same algorithm. So now I'm going to reduce it, the size, by 50%. So you can see the size changes. Here we're reducing. We started with an 800 by 800 image. Oh no, don't tell me that's a stop sign again. Ah, URL, yes. Wrong here. I need to go back up and reload the image. Ah, no. That's actually what I can avoid by doing this. I don't want to load the stop sign anymore. So here 1000, then 999, 996. Here you can see the output of a previous image that I had. This is the original image of Taipei 101. This is the seam carved image. When we zoom in by a factor of 50%, as you can see, we still maintain most of the Taipei 101 building, which is the part that we're really interested in. Here, if I do a normal zoom to the same size, then the image is sort of not so interesting. A lot of details on Taipei 101 will have disappeared. And here we can carve in 2 dimensions, and rows and columns. Before the first one, I only carved the columns, not the rows. So this one here is now 1 column removed, then 1 row removed. 1 column removed, then 1 row removed. And you can see, I zoom in, I still see more of the interesting part, which is the Taipei 101 building. Another interesting thing that we can do with this particular algorithm is I can use it to remove, for example, unwanted artifacts. Like people have developed whole applications for that, so that you can remove your ex-husband or ex-wife from the image because you don't want to see them anymore. Or if somebody walked behind you while you took a picture of a selfie of the Eiffel Tower in Paris, you can remove these people. And we can do that by having a user interface where the user can draw and select the regions of the image that they're not interested in, and we simply set the gradient on those pixels then that were selected by the user. We set those pixel gradients to automatically to 0, which means that the seam carving algorithm will then be very keen on removing them, because they would show. So even though there may be, if you don't want type A 101, you simply paint over here and select in the user interface, then the algorithm, when we calculate the gradient, afterwards it will replace all the gradients, Sobel edge output in this part of the image with 0. And then that is much more likely area for the algorithm to remove. So that way we can remove artifacts from an image. So this is another application of the same algorithm. Now, one thing that we haven't discussed yet. Yeah, this is still going for a while. Is when we remove the image, when we remove the seam, then right now, if you can look at the algorithm, if you look at the algorithm, then I carve the seam, then I rotate the image by 90 degrees, then I carve the seam again, and carve seam will actually remove the path. But if I want to, so we go through the entire process every time we want to remove a row or a column. That may seem excessive, but you would think that if you look at the output of our sum array, if you look at the output here and you want to remove 2 columns instead of just a single column, then you may think saying, oh, 136 and 156, those are the 2 minimum ones. So first I remove 136, then I remove 156. However, that doesn't work. I have to completely recalculate the gradients of the image, as well as the path that I want to remove. Because here, for example, 136, if I look at the path, I'm going to remove this pixel. So if I remove the 136 path, I will remove this pixel, I will remove 102, 99, 64, and 17. If I now want to remove 156, then that's not going to work, because now pixel 102, the path through to 156 also goes through the same pixel 102. But that pixel is already gone, so I cannot remove it again, which is why I need to recalculate the carve, the sum array, the dynamic programming cache, every time after I remove one pixel, one seam. After I remove a column or a row, I have to recalculate the entire image, not just part of it. Now in theory, you could optimize that, but it's not worth it for larger images. Like you could say, since this is only 5 rows here, right? 1, 2, 3, 4, 5. This pixel, even if it goes all the way to the right here, even if it always goes to the right, then it will not interfere with any path that is, let's say, going here up to row for this pixel. Let's say if we start with 249, 162, 99, 88, and I start, if this is the minimum path, if this is my minimum here that I removed, then all the I won't be able to remove any pixels from this path here. So if the minimum was here 100 and this would be 99, then I can actually safely remove both at the same time. But that's a lot of extra processing. It is usually faster to just recalculate the dynamic programming cache for the image. Also, we recalculate the gradients because now the similarity between the pixels has changed. So let's see how far we got. Okay, so here we have the shape. First I removed 500 columns. I didn't actually iterate it like that. I removed 500 columns first and then 500 rows. That is also right? No, how come I have 500? Oh, I think I made a mistake. It's now removing the rows. It seems like it's completely getting rid of the image now, reducing the columns. Reducing the columns twice. First from 1000 to 500, then from 500 down to 0. No, actually okay. Yeah, that's correct. No, so then let's see what the output looks like. Oh, I used the wrong image. That image, not the one I wanted from the Kaohsiung. Where did Kaohsiung go? Ah, yeah. I wanted to take that picture, but yeah, so that's a correct image. And then where's that stop sign? That caused me a lot of problems now because it overrode. So here's our gradient image. Now let me just run, but I won't run it through the entire thing again because it'll take a little bit too long. So here we want to carve the scene. Here's the URL, we get the image, we read it, and then that's the original size. Then I want the scale. So instead of shrinking it by 500 by 500, I just scale it to a 640 by 480 image first, and then I remove 80 pixels, 80 rows, 80 columns, just so that it runs a little bit faster. So it should go to 400 now. Yeah. And then let's see. So here's our resized images. Then you can see, even though we zoom in, the ah. It should be 480, 640, not the other way around. New height is 480. This one is 640. Okay, while we're waiting for the program to finish, also bear in mind the assignment is due, as well as we have the midterm next week on Wednesday from 9 to 12 o'clock, also administered via Discord. So you can take it online if you want to, or you can take it in the classroom. Both are fine. And I will post a sample midterm exam later today. here's the scaled thing now, and this one is just scaling correctly. But you can see as we removed columns, the pagoda actually looks pretty nice still prominent in the foreground. Mostly the not so interesting parts of the image have been removed. That tower is still there, and here, this one. Oh no, I lost my connection now. Oh, no, it's still running. And here you have our smart sampling algorithm, our smart zoom algorithm. Right? You can see a lot more of the pagoda stays in the image. The parts that are interesting in that sense are still much more prominent than in the zoomed image here. So now I can move it to half the size, but or you can run it yourself afterwards. And I think it's in practice probably a little bit better if you do column removal than a row, than a column, than a row. I just wanted to show both impacts here. So I remove all the columns first, then the rows for after that. Not sure about that. We'd have to experiment with some more images. Okay, so let me run this, and that's it for the class today. I will see you next week on Monday, and we will not discuss any new material on Monday, but then on Wednesday we will have the midterm. Let me see what the date would be. Sorry, not next, I mean, not on the 25th, but the 1st. Right, 1st November is the midterm exam. Okay, good. So bye bye.